Okay, so hi everybody, welcome back, and we're going to start the new session now, and our next speaker is Ora Entin-Wohlman from Tel Aviv University, and she's going to talk about spin-active weak links. בבקשה.
Okay, I don't have a nice joke, only the joke about somebody that asked, that was allocated 10 minutes and was asking, I think it was Mark Twain, how can he say all that he wants to say in 10 minutes, and Mark Twain said, say it very, very slowly. So I hope I will stay in time. So, my talk is about spin-active weak links, and it belongs to, let us say, the general field of spintronics, if you wish, magnetoelectronics, which is the hope to have technology based on electronic and spin, that is to say about the charge and the magnetic moment of the single electron. So, of course, I cannot propose to you any technological advances, but I'll try to say to you what we do. Okay, so one may say that it all started with a proposal by Data and Das from 1990 about a spin transistor. And that spin transistor looks like a regular transistor. Namely, we have two source and drain, and we have a gate by which we can change something. And the idea is that the source and the drain are ferromagnetic. Let's say that the spins are up on both sides. And with this gate voltage, we can change the spin-orbit interaction in the blue area, which is like the way they do it in a regular spin, in a regular transistor, sorry. And as the electrons go from this source towards the drain, they change the direction of their spin because of the spin-orbit interaction that we can modulate with the gate voltage. I hope to show you how. And if they come to the other, to the drain, with the spin being in that direction, they cannot enter that ferromagnet. And if we change the spin-orbit interaction, then they will do, let's say, full circle, and then they can enter it. So that was the proposal. I think it is not realized so far experimentally. But then came lots of interesting effects due to spin-orbit interaction, like the spin-hole effect, by which if we send currents through a whole bar with spin-orbit interaction, we can create different populations of, say, electronic spin on the two sides. There are then another direction which is followed in the Weizmann Institute by Ron Amnon, where it can prove or can measure spin selectivity when electrons go through a helical molecule. Again, another direction. And I would like to show you that by DC spin, we can generate DC spin by an AC electric field. And another direction that we follow is what happens when there is a weak link which is spin active, namely it has spin orbit interaction, and it couples to superconductors. Should I move this? Okay. So let me remind you what is the spin-orbit interaction, though everybody knows it. So the spin-orbit interaction term comes when you expand the Dirac-Hamiltonian to lowest possible order in the speed of light, and then you obtain a bunch of terms, but the one that I am interested in is this term, which has the spin, or the magnetic moment, cross the momentum, the linear momentum, and the dot is for the gradient of the potential. And this, if you look at this, then if the system is rotationally symmetric, or the potential is rotationally symmetric, then you can write it in terms of simply the spin dot the angular momentum. The angular momentum is the derivative of the potential cross the linear momentum. In my case, in the thing that I would like to discuss, S is again the spin. The gradient of the potential is the electric field that you can apply with a gate voltage. So it's minus the electric field. Again, cross the linear momentum. And this sometimes in 2 dimensions, at least, is called the Rashba interaction. So this is the interaction that will play a role here. So here it is again. And as I said, in particular, I'm going to be interested in 2-dimensional or even pseudo 1-dimensional weak links. And the situation is described here because you have an electric field, you have the momentum, which is the direction of propagation in the weak link, and you have the spin, which I am going to call sigma. And if you look at this expression for the Rashba interaction, then you see that you can describe it in terms of an effective magnetic field, which is the electric field cross the momentum. And then you might have thought that you are with a Zeeman interaction and you are in business and you can generate spin direction. However, the only difference is that this interaction does not break time reversal symmetry. Contrary to what happens with the Zeeman interaction. And the reason is that one direction of the spin field this magnetic field and the other projection in the inverse direction. So this will be a very important player. Spin-orbit interaction does not break time reversal symmetry, and therefore it is hard to think how it can create polarization, magnetic polarization, or spin accumulation.
It's actually not so, it's not pseudo-magnetic field. It's the magnetic field in the frame of the particle.
This is correct. It is a magnetic field, but at the end of the day, when you take the 2 spin components, then it conserves time reversal, which is what is important. So how can one experimentally control the spin-orbit interaction? And here I would like to mention, just to mention the notation that I'm going to use. So the Rashba interaction in its full glory has some parameter which I'm going to call K sub SO, SO for spin orbit. This is the spin orbit strength, or the coupling. Then there is the effective mass of the electron that moves through the system. And then you have the momentum, Py and Px, because you are in a plane, and the sigma is going to be the Pauli matrix all the time. And the way the spin orbit coupling is measured is by applying a magnetic field, a true magnetic field. And it was done in an experiment in the 90s, and even before, in which they measure the gas van Alphen oscillations of the conductance, the resistance, as a function of a true magnetic field. But when you measure the gas van Alphen oscillation in a material which has a spin-orbit interaction, then you find bits due to the spin orbit. And from those bits, with the help of a model, you can extract the spin orbit coupling strength. And moreover, what you can show, and this is shown on the left side, you can show that by changing the electric field that creates the spin orbit interaction, you change indeed the spin orbit strength. So that was a way to measure it, done in NTT in Japan. So now I'm going to come back to the question whether we can induce spin polarization, polarize the material just by spin-orbit interaction. So the basic system that I would like to consider is a junction between two metals that are not magnetic. If they are magnetic, then there is no wonder. Then there is some potential barrier or quantum dot, if you wish, and then the electron goes from one side to the other. And if you have a spin-orbit interaction only in the weakly connecting the two terminals, then there is a famous exact result of Bardarson from 2008 that in such a system, spin-orbit interaction cannot induce any spin polarization. And the reason, I will not go into all the proof of the theorem because it's kind of technical, but the reason is that as the electron goes through the spin-orbit active link, it rotates because of the spin orbit. But one spin projection rotates this way and the other rotates that way, and then when they cross the weak link and come to the other side, the result is zero interference. And therefore, the conductance or the scattering matrix cannot induce polarization. So you must break time reversal symmetry in some way in order to have any use of the spin-orbit interaction. So I'll skip this. And now I'm coming to something which is important for us, coming from Tel Aviv University, which is related to the talk of Yossi Avron. This is called the Aharonov-Kasher phase. Aharonov has a very famous name, professor in Tel Aviv University, and Kasher, who like Zak, was my teacher in the Technion, was also a professor in Tel Aviv University. So what is this phase? So let us go back to the Rashba-Hamiltonian. If we look at the Rashba-Hamiltonian and realize that it looks like a Zeeman-Hamiltonian, we can try to think about it as related to some vector potential, which when we add it to the kinetic energy, we can gauge it out all together. Yeah, very nice, very simple, but it doesn't work. And why doesn't it work? Because of Yossi. Because I'll tell you my version of what I understand from you. It doesn't work because when you do what I just recommended to do, namely take this spin-orbit interaction, add it to the kinetic energy, and complete the square, as they say, then it's very nice, but you get as a result a phase on the wave function, which is some effective magnetic field, if you wish, dot the Pauli matrices. And the problem with this phase is that it's a 2x2 matrix, and matrices should not commute. And therefore, and now I will present you my bad talent as a drawer. Namely, if you want to go from one point to the other via this phase, and let me come here a little bit. Suppose you want to go from this point to this point. Then this one has some phase, let's say phi, that is the radial phase. So you have this matrix as the propagator to go from this point to that point.
Oh, can you speak to the microphone?
So you have the propagator, which is a phase factor. And then you say, I'm going to increase a little bit the radial phase with a little delta phi. So I have to multiply the two propagators. And I can do it step by step with little delta phi. And at the end of the day, what happens is the following. If I started with an effective magnetic field, this vector is in, let's say, in the xy plane, then after I go another delta phi, it will start to go out of the plane because of the product of the Pauli matrices. And therefore, if you want to put your electron on a circle, for example, on the Bloch sphere, with a magnetic field, effective magnetic field that is, let's say, radial, then once you go a little bit, it will start going out of the plane. The magnetic field will go out of the plane. And this going out of the plane is called the Aharonov-Kasher phase. So having said all this, the question is how do we measure this Aharonov-Kasher phase, or how do we calculate? So here I present to you a measurement.
So at the beginning I got the impression that you wanted to present a problem. It's not a problem, it's just the Aharonov-Kasher effect, right?
My point at the end of the day, if I get there, is to show you how you can measure the Aharonov-Kasher phase. So let me tell you how it was measured first. So it was measured again by putting a magnetic field. And this is a measurement that was done on Aharonov bomb ring. And again, what you find that the spin-orbit interaction induce a kind of whirl or beats in the Aharonov-Kasher, in the Aharonov bomb oscillation, again. But our point was that not by doing any interference experiment, just by doing tunneling experiment, just by measuring the conductance between two terminals, we can induce the Aharonov-Kasher phase. So this is what I want to show. So how can we do this? The idea is, let's calculate the conductance through this weak link. And the conductance is given, as we all know, by the transmission absolute value squared. And write it better, that it's basically the product of the propagator to go from one side times the propagator to go to the other side. And the next step in the calculation is let's calculate what is the propagator. So this calculation is done in the presence of a Zeeman field on top of the spin-orbit interaction in order to break time reversal symmetry. And the result is, and let me first tell you what will be the result. As I said, by the Aharonov-Kasher phase, one direction of the spin rotate this way as they go, and the other rotate in the other direction. If we have also a Zeeman field, and I will say at which direction in a minute, then the one that goes this way gets a little bit more because of the Zeeman, and the one that goes in the other direction gets a little bit less. And therefore, the interference in a non-interference system between the two spin components will affect the conductance. Now, how it is done? So you have to calculate the propagator, so you calculate it, and then you have to calculate the this product of the propagator times the propagator trace over the spin directions. Let me first tell you what is the result if there is no magnetic field. If there is no magnetic field, it is not the spin orbit will not affect totally. It will, because it changes the Fermi energy in the weak link. It is a second order effect. The coupling, the spin orbit coupling is much smaller usually than the Fermi wavelength, wave vector. So what happened? So what happens when you calculate the propagator in the absence of a magnetic field is that you find something which is going to stay there and which is a little twist on the Fermi wave vector by the spin-orbit coupling times the Aharonov-Kasher phase. And when you take absolute value squared of this thing, then this phase disappears. There is no dependence on the length of the weak link, and you get something which is not so useful. However, if there is a magnetic field, and moreover, the magnetic field is not in the direction of the pseudo-magnetic field of the spin-orbit interaction, because if it is, then it will do nothing. So the best that the magnetic field will be perpendicular to the direction of the magnetic field of the induced by the spin-orbit interaction. Then the propagator is more complicated, but you can calculate it. And then once you finish the calculation, then you find the following result. The direction of the magnetic field induced by the spin-orbit interaction in this model is along Z. So you have something along Z which is changed a little bit because of the spin-orbit interaction. And then you have the component normal to the magnetic field induced by the spin-orbit interaction, which is also, this one is also rather small. So if you combine these two terms, you find that the result is isotropic in the Zeeman field, as it should. However, what you find from the mismatch of the interfering two-spin component is this term, which is proportional to the magnetic field, to the Zeeman field, times something which is a real phase, because it depends on the length of the weak link. This is what I call D here, and the spin-orbit strength. So by applying magnetic field, it's another way to measure the spin-orbit coupling without, preparing a Aharonov-Bohm ring or other device. If the magnetic field is not totally normal to the magnetic field of the spin-orbit interaction, then you have another factor of sine squared. Theta is the angle between the magnetic field and the magnetic field of the spin-orbit interaction. So this was one proposal that we did. If somebody is interested in more details, then after a long fight with PRL, we succeeded and we got it into PRL. Okay. Now, the question we asked is what happens if the leads are superconducting? And I'm talking about simple BCS superconducting leads. What will happen? So let me tell you the result before I'll show you what we did. What I am going to show you is what happens to the Josephson current. The Josephson current, although we all call it current, it's not really a current because it is there in the absence of a bias. It is there because you have two superconductors with different phases of the superconducting order parameter. Now we all know that in case of simple BCS, the amplitude of the Josephson current of course depends on delta, on the superconducting order parameters. It will not be there if delta is 0. However, the other parameters are like the conductance in the normal state. So it's kind of a rule of the thumb. You know the conductance in the normal state of a junction. The Josephson current is proportional to it. Now, I tried to tell you and to convince you that in the conductance of the normal state of a junction is not affected by spin-orbit interaction. However, the Josephson amplitude does. Namely, the spin-orbit interaction does enter into the amplitude of the Josephson current. So I can now ask you, what do you expect? will it increase or decrease the Josephson amplitude? Decrease, of course. I mean, Josephson is the current of the Cooper pairs. The Cooper pairs in the BCS are nicely two electrons with anti-parallel spins. Spin-orbit interaction is going to ruin this. So, of course, it will reduce it. And that's the result. But let's look at it in more detail. So, as I said, first I show you the result. And what you see in this, I'm afraid to touch it because what you see here is the Josephson amplitude as function of the Aharonov-Kasher phase, which is the length of the junction times the spin-orbit coupling. So first you see that it oscillates. It oscillates because it's interference effect, although the system, you know, it's a straight junction. Still, there is interference of the two spin directions. And
Ora, what is the dimension of the junction? It's two-dimensional?
One-dimensional for me.
1D. So there are no transversal modes or anything?
No. It's the interference of the two members of the Cooper pair. I'll show you in more detail in a minute.
Okay.
But what you see here is the interference, and the interference disappears as you increase the spin-orbit strength. So how can you see it? As I told you, the Hamiltonian, the system is very simple. You have the left and the right BCS superconductors. You have tunneling, and the tunneling is spin-orbit affected. That's the entire story. And then you can ask yourself, so what will happen? So this is a classical version of this quantum problem. Suppose you're in suppose the two superconductors are normal above Tc. Then you send one electron, it rotates a little bit because the weak link is spin orbit active, and it comes to the other normal in a little bit a different direction. But what happens when you send the Cooper pair? The Cooper pair is made up of up and down spins in this picture. So let's assume that first goes this electron with the up. I'll come later to the question that comes to one's mind, namely what happens if the two electrons somehow are at the same point on the weak link, and then they should be affected by some Coulomb interaction. I'll come to it. Anyhow, first let's assume the first one goes and it rotates a little bit. Then comes the other one and it rotates in the other way around because it is a down spin. So when we go into the superconductor, the drain, then it's not anymore a nice Cooper pair because you have the component of the PUA. And that's the reason why we diminish the Josephson current amplitude. So here is the result of the calculation. As I told you, it's based on the Hamiltonian, and it's not so complicated. But what you find is the following. This funny W is the propagator absolute, propagator times its complex conjugate. But in the, if there is no superconductor, then this term is not there. And then if you sum a unitary matrix like the spin orbit phase factor, then you get 1, and there is no effect on the spin orbit interaction. But because of this change of the Cooper pair, you have to subtract from the propagator the transmission probability to go and reverse the spin. And this is what reduces the Josephson amplitude. And if you look at this, then it is similar to what we found when you put a magnetic field, the same effect of the Aharonov-Kasher phase, that appeared in the presence of a magnetic field in a normal junction appear here in the presence of two superconducting leads. And this is a paper that we did in 2016. And then there came the question, what happens if the two electrons of the Cooper pair meet when they go through the weak link? So this is a rather difficult problem. And at the end of the day, we decided to do it as follows. Let's assume that the junction includes also a quantum dot. And then let's assume that the electron meet, the two electrons with the two spin direction meet on the quantum dot. And let's see what this will, and on the quantum dot, they of course have Coulomb repulsion if they meet. So let's try to estimate what will happen to the Josephson amplitude. So let me tell you the end result. So now we replace the junction by weak link and a quantum dot on the way, and calculated the same stuff, and assume that if it happens that the two electrons are on the quantum dot, then they suffer from the Hubbard interaction, and they have to pay. So what one finds is, as expected, it is not so good for the result. I mean, the spin orbit effect is diminished because of all these complications on the way. But still, it is there. It does not go totally to zero. What you see here, I'll show you this in the expression. So the spin precession can be described in this formula as coming from two contributions. There is the single electron contribution, which is not affected by the Coulomb interaction. And by single electron contribution, I mean that the electron go through the junction one by one. First one comes, goes out, and the second one. And that's the result I showed you before. But if it so happens that the second electron comes in before the first one left the junction, then they suffer from Coulomb interaction, and this is called the double electron channel, and this is the name we invented, and it depends on the Coulomb energy, which is here noted by U. And the total result of the Josephson current can be expressed as follows. There is the contribution of the single electron, which is the probability to go from left to right coherently. And then, because of the Pauli principle, because when the two electrons meet on the dot, they suffer from interaction, the probability to go in the double channel when, as I said, one electron did not yet went out, did not yet go out, and the other one came after it. And then we lose the coherence, and the probability is to go from left to the dot times the probability to go from dot to the right. And the combination of these two reduce the Josephson amplitude. So I hope it was quite clear. I did it fast. So again, you can ask for my help. So I think I finished. And let me present you our team. And the team consists of Professor Aharony, who is here, and our two Swedish guys, Robert Schechter, who is from the Ukraine, and the other Swedish guy is Mats Jonsson, who is in Scotland. And another work that we did on this, in this direction is considering the possibility to polarize electrons when they go through helical molecule like DNA. And on that work, we collaborate with Yasuhiro Otsumi from the Mi University in Japan. Thank you.
Yeah, thank you, Ora. Any questions?
So you mentioned that because we were discussing a singlet superconductor, spin-orbit interaction can only reduce the Josephson effect. What would happen if it were a triplet superconductor? do you have any anticipation?
No. Now, what we want now to look at is in the, not really what you said, but what we want now to do, to see the polarization, because we polarize the Cooper pair. So our idea now is to do the following complex calculation. Again, the tunnel junction, which is spin orbit active, but inside there is a quantum dot, and that quantum dot has two levels. If there are two levels, that we know from our other work on the helical molecules. If there are two orbitals on the quantum dot, then we think that we can polarize the pairs. And then maybe I'll have an answer to your question.
I have a question. On one of your slides shows the Josephson current, and then the spin-orbit coupling seems to make change sign of the Josephson current. So in one of your slides, you showed like J phi divided by J0 phi, depending on the x-axis, like spin-orbit coupling, something like that. And in one of the current seems to change the sign from the original one. How do I intuitively understand that? Is it because the spin-orbit coupling generates the...
Thank you for the question. It's an important point. Namely, we can change the sign of the Josephson current by changing the spin-orbit coupling or the length. But this is, I view it as part of the oscillation as function. I'm talking about a phase, the Aharonov-Kasher phase. So a phase, if it appears with the distance, then you want to see something which oscillates. So if it oscillates, it goes sometimes down. And so the current will go to the other. But it's not a current. So Josephson current is not a current. It's not a current. It's an amplitude.
I have other questions. What would be the effect of the decurrence? Can you, I guess your formalisms assume everything is current, but let's say the link has decurrence. Can you tell the effect of decurrence?
Of decoherence,
yeah?
It will not go. It will not be good. If you ask me if I put it into the equation, the answer is no. But what do you expect?
One of your slides shows difference between the conductance without magnetic field and with magnetic field, and you showed that it depends on the strength of the spin-orbit coupling. Let's say I have a decurrence, which you cannot avoid in your experiment, I guess. Would your formula still valid, or
You see, whenever you want to deal with decoherence, in a way, you add some imaginary term or imaginary time, if you wish, to your consideration. And then the question is how you model it. You can model it by some exponential with time. I didn't do it, but the answer, whether it will reduce the effect for sure.
So when you make a superconducting tunnel junction, you have two types of tunnelings. One is Josephson tunneling, and the other one is single particle tunneling. But when you explain your picture, you use the unwrapped reflection. That is kinds of single particle tunneling, not co-tunneling of Josephson tunneling. So why do you use the single particle tunneling when you describe the Josephson tunneling?
You mean that we should include also pair tunneling?
Pair tunneling is Josephson tunneling, but you introduce the single particle tunneling, like unwrapped reflection, to describe your system.
Well, first, what we did was to assume single electron, not particle, single electron. Namely, you know, superconductivity, the way you treat it by Bogoliubov diagonalization, so you have to work with quasi-particles. So it's not quasi-particle tunneling, it's electron tunneling. So part of it is superconducting Josephson current, and part of it is quasi-particle current, which I did not present it because the quasi-particle current is not there if you don't have a bias voltage. Right?
But my question is, Andreev reflection is type of a single particle tunnel, it's not co-tunneling.
Yes, but since we calculated current, I give you the result of the current that includes whatever it is there in the absence of bias voltage and at very low temperature.
Okay, so we're out of time, so let's thank Ora again, and